Okay. So for steel, it will be more extensive lah. Okay. Steel design, we will talk about steel classification, section classification. We will talk about bending. We will talk about the effects of restraint on bending and buckling. And then we will do column design, just like very similar to RC design. Okay. We will talk about beam, we will talk about column. Okay. The only difference is for steel design, we will cover connection juga. Okay. Bolted connection and welded connections. And we will also talk about truss design. Okay. Because obviously trusses are normally made of steel. Okay.
Excuse me, doctor.
Yeah.
The screen is blank.
Yeah. Don't worry. I'm right now. I'm not displaying anything. I will share the syllabus. I'm going through the syllabus with you right now, but I didn't display it on screen because I don't have it on my tablet. Okay. I'll share the syllabus later. Okay. All right. Now, in terms of assessment, very similar to RC design as well. We will have 3 tests: test 1, test 2, and test 3. Okay, yeah, so we have 3 tests: test 1, test 2, and test 3. Each test will be 10%. There will be a short assignment, 5% only. And then there will be a project as well, like what you did for RC. Okay, there will be a project. For the project, you have to hand in a report, 15%. And you will also have to do a presentation, 10%. Okay. So altogether, there will be 6 assessments now. Okay, 6 assessments. 3 tests, 1 assignment, 1 project report, and 1 presentation. Okay. Altogether, these will form your carry marks. Okay, these will form your carry marks. And your carry marks will be 60%. That means your final exam will be 40%. For the final exam, probably I will give you, I don't know yet, maybe 3, maybe 2. No, maybe 3 to 4 questions. Okay. Final exam, 40%. It will be 3 to 4 questions. Most of them will be steel design and 1 will be timber design. All right. That's it. That's it for the planning of this course. Okay. So like I said, I will share the syllabus with you after this. All right. So now we can head on to the first topic, or more. Well, it's not the first topic. It's more like the introduction. Okay. Right. Can you see my screen? Let me know. Can you use your mic to let me know, because now I'm not looking at Google Meet. So even if you do thumbs up on the Google Meet, I cannot see it.
Yes.
Boleh nampak? Okay, thank you. All right. Okay. So the slides I will share with you as well later. All right. I don't share the slides earlier. Yeah, as you know, I share the slides later, so that right now you can look at my slides only and you can follow as I go along, and you take your notes juga. All right. Okay, so steel design. So steel design is based on Eurocode 3. Eurocode 3 is equivalent to the thing I mentioned here, BSEN 1993. That's basically Eurocode 3. Okay. So for the first course, I'm going to go through quickly. For the first class, I'll go through quickly the background to Eurocodes and how buildings behave. So this part will be very similar. Will be very similar to what you did for RC design. Okay, with minor changes. All right. Okay. How do I go next page? Okay. All right. So again, this is the Eurocode nomenclature. So the Part two, the words they use, okay, in Eurocode. Okay. British Standard is what we used last time, but now we've shifted to Eurocode, so you have to get used to Eurocode. Okay. So the word check, we don't use anymore. We use verify. The word loading, we don't use anymore, but rather we replace loads with actions. But sometimes we still use it interchangeably. You should know what it means. Loads basically means actions. I will use them interchangeably. All right. Dead loads means permanent actions. Live load means variable actions. Okay. You also have your frequency value, but that one you don't worry about it. We are not going to talk about it in this class. Quasi permanent value, it's also for SLS chat. We don't worry about it in this class. Okay. And then if you read Eurocode, you will find that the decimal point 2.65 is replaced by comma. They use comma as decimal point in Eurocode. Okay, so it's just something for you to bear in mind. Okay. Okay, so this is how Eurocode is presented to you. Okay, for steel design, right? For the steel design, basically you'll be interested in four different Eurocodes. All right, you have Eurocode 0, which is the basis of your structural design. So this is where all your partial safety factor, all those stuff come in, okay? And then you have Eurocode 1, which is action on structures. So Eurocode 1 is more towards the loading. Actions means loading. So Eurocode 1 means it talks about the loadings on your structures. And finally, Eurocode 3. Okay, Eurocode 3, design of steel structures, EC3. Okay, so that's going to be our main focus. Later in the course, we will talk about timber design as well. So that will be Eurocode 5, but we worry about that when we come to it. All right. So that's next, don't worry. Okay, basis of structure design. Okay, so when we do design according to Eurocode, there are two things that we have to check. So this slide is the same slide that you've seen in RC Designer, so it's the same thing. The next few slides pull up. The next few slides as well. Similar slides that you've seen in RC Design. Okay, so limit state design. So basically, when you do design for a structure, you have to verify or check it for two different states. Okay, there's the ultimate limit state, and there's the serviceability limit state. Okay. So ultimate limit state, you check it to prevent collapse of the structure. And this is quite important because you are preventing collapse. So you are designing it to ensure safety of the people and the structure. Now, there is also a second type of limit state that you have to check, which is the serviceability limit state. You check this to ensure the structure is usable. So for SLS, you don't actually design to make sure it doesn't collapse. It's more towards usability and functionality of the structure. Okay. Okay. So now I'm going to just show you the difference between ULS and SLS. Okay. So ULS are things like so ULS, you are designing it to prevent collapse. Okay. Therefore, you need a higher factor of safety. You have to make sure the design is elastic. And basically, when you do your checks, you check against strength. You make sure the beam and column hasn't yielded, hasn't buckled, and is stable. Okay, so there are four pictures here. These are basically what you are trying to prevent. Okay, when you do ULS design. The one at the top, lateral torsional buckling. Okay, the picture at the top, lateral torsional buckling. that is what we are going to, that is what concerns us when we design beams, steel beams for buckling, okay? So you will learn how to design to prevent that from occurring, okay? Lateral torsional buckling. And then the picture at the bottom left is a connection that has failed. You can see 2 of the bolts are still in, but the other 2 are missing, okay? So the bolts have failed. So you will learn how to design bolted connection as well, okay? Now, SLS is slightly different. So you also have to do SLS checks. Although for this course, we are not going to talk too much about SLS, okay? But when you start working, this is something you have to check lah. All right. So SLS, you do this check to make sure, not to prevent collapse, but to make sure the building is still usable, functional, okay? So the checks are things like floor deflection, floor vibration, and to make sure the thing doesn't crack, your structure doesn't crack. All right. So here are some pictures of SLS failures. So because when you do SLS checks, you are not checking it against collapse. You are just checking it to make sure it doesn't crack, make sure it doesn't deflect too much. So the factor of safety is also lower. Okay. Okay. So let me get my pen out. Wait, let me get my pen. Right. Wait, something kat sini. Yeah. Okay. So partial safety factor and verification. Okay. Now, all right. When I was marking your RC design final exam paper, okay, I noticed some of you made mistakes with this. So make sure you memorize this. So I repeat myself, when I was checking your RC design final exam punya answer scripts, some of you've forgotten this formula. So this on this page, the most important thing is this. Screen right. Okay. Why do you take picture? No, I don't want to take picture. Okay. This thing here. Make sure you memorize this. All right. Make sure you memorize this. Some of you forgotten during the final exam for RCD. Some of you use 1.5 GK, 1.35 QK, which is the opposite. Okay. Some of you use 1.15. Some of you use, I don't know. I've seen different variations. Okay. But the correct one is 1.35 GK, 1.5 QK. GK is the permanent action or dead load. QK is variable action or life load. Okay. So you have to remember this formula. 1.35 GK, 1.5 QK. GK is permanent action. QK is variable action. Okay. This is the most important formula on this page that you have to memorize. Okay. Next. Okay. So there, I've actually got a definition here. All right. So from Eurocode 1, okay, actions or loadings on structures. So if I mention here, you can see GK is permanent action or dead load. QK is variable action or the life load. Okay. Now, on a typical building, you have dead load, such as the roof structure, such as the floor, such as the wall. These are all dead load. Okay. Your beam punya self weight is also a form of dead load. Okay. Basically, dead load is anything in the structure. Okay. So dead load can be the beam or the column self weight. Okay. The beam and the column self weight. It can also be anything that's really fixed to the structure. So anything that's fixed to the structure, for example, your floor tiles, your carpet, anything that is fixed to the structure that you cannot remove easily. Anything that is fixed to the structure that cannot be moved away easily is considered dead load or permanent action. Live load are loadings or actions, variable actions, or live load are loads that can vary and that can move around. Or vary. Okay, so live loads or variable action are loads that can move around or it can vary in magnitude. In magnitude. Okay. So for example, live load on the roof will be snow. If let's say you live in a Western country, the live load on the roof may be snow. Now, sometimes when it's not snowing heavily, the snow load will be low. But sometimes when it snows heavily, then the snow load gets high. So you have a difference in the magnitude of the snow load. Okay. Another type of live load will be people, or furniture on the on the slab. Now, imagine a BT. Imagine a BT. Okay, billet tutorial. Okay, the live load in that BT will be you lah. You, people like yourself. When the BT is empty, then the magnitude of the variable action is very low, zero, close to zero. Okay, you might have one rat or two rats, or you might have a stray dog going in the room. Okay, but the variable action will be very low. Now, when the BT is being used, then there will be students in it. Then the variable action will increase. Okay, so variable action is something that can move around. You can move out of the room. You can come back into the room. So variable action are loads that can move easily, and it can vary in magnitude. Some students weigh 50 kilos. Some students weigh 100 kilos. So the magnitude can vary. Okay. So these are the difference between permanent and variable actions or dead and live loads. Is this clear? Nanti project. Waktu project you have to I will give you a building. During the project, I will give you a building. You have to identify the dead and live load on the building as well. So make sure you know the difference between the two. Okay. Right, next page. Okay, now this is the table. This is a table from Eurocode 1 on the examples of variable actions on a floor. Okay, so A1 is self-contained dwelling units. So these are like Soho or small apartments where one or two people are staying in it. Yeah, so you know those Soho units. What do they call it? Soho units. They also call it. There's a name for it. So studio apartments. Okay, so A1 are places like studio apartments or Soho units where it's a room for people to live in, but there's no partition for bedroom. Okay, so the place where the living room is also the kitchen, is also the bedroom. Okay, so for those ones, you use a QCare of 1.5. Now, if you have a house where you have a separate bedroom, bedroom, then you use 1.5 for the bedroom as well. If you have a bedroom in hotel pula or hospital wards and toilets in there, then you use 2. So basically, as you go down the table, the variable, the magnitude goes up and up lah. Okay. So you have shopping areas, you have storage, you have, yeah, a lot of different choices for you to choose from here. Yeah, okay. All right. Okay, next. Okay, load path. So this is a very common question that I get during when you're doing a project. Okay. So in a general building, we look at the picture on the left. Okay, look at the picture on the left. So those are the common components in your building. So you have the roof sitting on the column. On the floors below, you have the slab sitting on the beam, and the beam is sitting on the column. Everything gets transferred down to foundation level. Okay. So when you're talking about load path, it's basically, so when you're talking about load path, it's basically the path that the load takes to get to foundation. Okay. So load path is the path that the load takes to get down to the foundation. Okay. The load will always choose the shortest. Load will choose the shortest route. Okay. You cannot tell the load how it will go. It will do its own thing. Okay. And it will always choose the shortest route to the foundation. Okay. Now, previously you've done RC building. Okay. This semester we're doing steel building. Now, in a steel building, the difference between steel and RC is normally in RC, you have to design the slab. In steel design, you don't actually have to design a slab because most slabs are RC. You very, very, very seldom get steel slabs. Okay, slab is always RC. Okay, so for steel design, we are only concerned about the column, and you cannot see yeah, and the beam. Okay, this X thing, this is bracing actually. Okay, so the steel element, so the steel elements in the building are normally the beam, the column, the bracing, and the truss and the connections. Okay, the slab itself is normally still RC. Okay, there. So these are your common components in a RC building. So you can see, sorry, no, in a steel building. So you can see the steel components are the beams, are the columns. For this building, you don't have the bracing. Okay, there's no bracing in this building. And then the roof structure is also steel. Okay, and generally it looks like this. Like if you take a detailed screenshot, that's basically all the steel elements. So the steel elements is supporting the concrete slab that is poured onto it. Okay. Okay. Next slide. So this is a new slide. The next few slides are new slides that I included because I realized that I didn't go through this with you clearly during the last semester for RC design. I should have done it, but I didn't. So now I've included it. Okay. So these are forces in a member. I think you might have done it. I think you must have done it during, I don't know, mechanics of solids. You might have done it inadvertently during mechanics of solids. Okay. But now I'm summarizing all the forces for you. so that you've got it handy in a few slides. Okay. So what are the typical forces that you get in a member or in an element, structure member? Okay. So the first one is tension. So tension is when you take a member and you pull it in two opposite directions. Yeah. So you can see this member is being pulled up and it's being pulled down. So the member goes into tension. When a member goes into tension, it will elongate or stretch. Means means it becomes longer lah. It will become longer basically. Okay. Now, tensile force. If you look at the tensile force, the force is acting in a straight line. Yeah, the force is acting in a straight line. That means it's a type of axial force. So tension, it's a type of axial force. Okay. So tension normally you will see in structures such as cables, ropes, or springs in a structure. Okay. And also in the convex region of beams in fracture. Okay. What does that mean? Later on, I will demonstrate what that means. Okay. So tension, normally you get it in bracing, you get it in hanging members, you get it in the diagonals of a truss, and you also get it in the convex region of beams in fracture. Okay. That last one I will explain later. All right. Now, the next slide is also an axial force, but it's different direction. It's compression. Now, compression, if you take a look, the force is also in a line. Okay, the force is also in a straight line. So it's also an axial force. So compression is also a type of axial force, but the direction is now opposite of tension. Instead of pulling, now you are pushing. Now you are pushing the member together. So when you push a member together, closer together, the member will get shorter or it will squash. Okay. So compression are usually observed in columns and also the concave regions of beams in fracture. Again, this one I will explain what it means later. All right. Okay, next. Okay, next. Bending or fracture. Okay, so bending carries the same meaning as fracture. We can use the words interchangeably, but they mean the same thing lah. Okay, fracture means bending lah. Okay. Now, bending is actually a combination of tension and compression working together, which creates the concave and the convex regions. Okay. Now, you remember just now, earlier, when I talk about tension and when I talk about compression, the axial tension, axial compression there. Axial tension, you get it in convex region of beams. Axial compression, you get it in concave regions of beams. What that means is when a beam goes into bending, when a beam goes into bending, do I have an example? Ada, tiada. I thought I included an example of this. Never mind. All right. Okay. So when a beam goes into bending, the beam bends, and then you have a section here. How do I delete? How to delete? Okay. Okay. When a beam goes into bending, you can see the bottom of the beam gets stretched. Yeah. The bottom of the beam becomes longer. the top of the beam gets squashed, becomes shorter. Yeah, you notice when the beam gets bent, the bottom becomes longer, it gets pulled, the top becomes shorter, it gets squashed. That means at the top, it goes into compression. In the bottom, it goes into tension. Okay, so the tension and compression is what causes bending in the beam. Okay, now when the beam is cantilevering, it's also bending, but the tension and compression gets reversed. Compression goes to the bottom, tension goes to the top. Okay, when it's cantilevering. Okay, so this is beam in fracture. Now there's another one, another type of force called shear. What exactly is a shear force? Now, you remember when we talk about tension, when we talk about compression, you remember it's a force that is acting in a straight line. Tension, it's being pulled. Compression, it's being squashed. But shear, you look at how shear acts. It's two perpendicular force, one from here, one from the left, one from the top, one from the bottom, in perpendicular direction, and not in a straight line. It's not in a straight line. Huh? You see here, it's not in a straight line. One is at the top, one is at the bottom. The other one is at the bottom. It shears and it basically slices your beam in half, your element. It basically slices your element in half cleanly. So this is shear. It normally, so shear normally is the highest at the ends of a beam. Okay, that's where the shear force is higher. At the ends of, you get high shear force like in the ends of the beam. Okay, next, you also have torsion. Torsion is a type of moment that twists your beam. So you have a moment going in anti-clockwise, and then you have another moment going clockwise at the bottom. Okay, so you have a moment going anti-clockwise at the top, and then you have a moment going clockwise. So anti-clockwise at the top, and then clockwise at the bottom. Two moments in different directions. It will cause tension. It will cause torsion in your beam. Okay, this is what causes torsion. So when you have torsion in your element, it basically causes the object to twist. All right, so that's torsion. So when you're designing beam or columns, you have to take all these forces into consideration. So meaning you have to check if your beam has compression, you have to check for compression. If your beam has tension, you have to check for tension. Or in some cases, combined loading. If your beam has compression together with torsion, then you have to check both. Okay, so combined means the earlier forces working or applied together in the element. So not just alone. So in this case, in this picture, you have compression, but you also have torsion. Okay, so that means if you design this member, you have to check it for compression, and then you have to check it for torsion. You cannot just check for one, okay, because it's undergoing two different forces. All right, so in real life, examples of combined forces in a member, so in beams. So in beams, the combined forces are flexure or bending and shear. In some cases, you also have torsion, but not very common, but sometimes you have to consider torsion. Now in columns, normally you have axial compression and flexure working together. Okay, so you have to check for both. So you remember RC? You remember RC design? When I ask you to do RC design, there's this table. There's a table like that, and then and then there's a table like that, and then it has lines that does that. You remember RC design? Okay, and then the bottom, for the bottom axis is N over FCK BD ka. And then the top axis is M over FCK BD squared, something like that. Okay, so this is RC, RC design last semester for column design. So column design, we need to use this table because the column is being subjected to the y-axis is flexure, the x-axis is axial compression. Okay, that's why you have two different forces. That's why you need to use this table to design your RC column. Okay, and I think that's it. That's it. That's it. Okay, so last slide. This is the last slide. Okay, so the design process, whenever you design any element, not just steel, RC as well, RC and timber as well. Okay, steel, RC, timber, the design process is this. You determine the loading or the actions. You do your analysis to get the forces. You select the section that works. You make sure the section has enough strength and stability. And then you design the connection. Okay, so this is the step-by-step on how to do elemental design for steel, for RC, for timber. Okay, so this is the last slide. And I think, okay, we can end the class here for today. Stay with me for a moment while I take your attendance. Bear with me for a second. Do attendance first.